More than 4 decades ago, a small spacecraft named Voyager 1 left Earth on a mission that many considered a long shot, an ambitious leap into the unknown. Its goal was to journey farther than any human-made object had ever gone before. When it lifted off in 1977, few could have imagined just how far it would travel or the mind-bending discoveries it would one day return to us. What began as a planetary exploration mission has become one of the most remarkable odysseys in the history of science and space travel. Voyager 1, the spacecraft that set off on its audacious journey nearly half a century ago, continues to redefine our understanding of space as it travels further into the unknown. Launched in 1977, its original mission was already ambitious: to explore the outermost planets of our solar system and send back data that would deepen our knowledge of these distant worlds. After spectacularly completing this task with flybys of Jupiter and Saturn that transformed planetary science, Voyager 1 did not stop. It pressed on, escaping the gravitational bonds of the Sun and heading into interstellar space. In 2012, it crossed the heliopause, the invisible frontier where the solar wind gives way to the interstellar medium, becoming the first human-made object to enter this uncharted domain. Now, over a decade later, and nearly 50 years since its launch, Voyager 1 is still returning data. Data so puzzling that it has forced scientists to rethink the very structure of our solar system's edge. Its latest transmissions have revealed strange, persistent fluctuations in the magnetic field, variations that contradict long-standing expectations about this region. Conventional models have predicted interstellar space beyond the heliosphere would be relatively calm, with steady, unchanging magnetic fields. Instead, Voyager 1's instruments are detecting weak but persistent rhythmic patterns, signals that seem anything but static. These findings suggest that the boundary between the solar wind and interstellar space may not be a simple fixed wall, but a dynamic, responsive structure, one that interacts with forces originating from deep within the galaxy. This new view challenges the traditional image of our solar system as a self-contained bubble adrift in a neutral interstellar sea. One emerging hypothesis is that these magnetic disturbances are being driven by energy streams or particle flows from beyond the solar system, currents emanating from distant regions of the Milky Way itself. If true, this would mean the heliopause acts more like a membrane than a barrier, an interface that flexes and ripples in response to pressures from the wider galaxy. Rather than being an isolated island, our solar system may be embedded in a vast interconnected network of cosmic forces. This concept aligns with the idea of cosmic filaments, enormous thread-like structures of gas, energy, and matter that crisscross galaxies, forming what cosmologists call the cosmic web. Until now, evidence for these vast structures has been largely indirect, drawn from observations of galaxy distributions on the largest scales. But Voyager 1's data might represent the first hint of their presence on a local physical scale. Such a possibility is paradigm-shifting. It opens the door to even more speculative questions. If energy or magnetic currents can cross light years, could they serve as a medium for interstellar communication? Might the strange fluctuations recorded by Voyager 1 be the echoes of some distant intelligence or even natural signals encoded in the galaxy's structure? Though these ideas teeter on the edge of science fiction, each new anomaly makes them less easily dismissed. What once sounded like fantasy now prompts serious scientific inquiry. Could the magnetic patterns Voyager 1 is detecting represent a universal messaging system, natural or artificial, stretching across stars and galaxies? The implications are profound and unsettling, igniting debates among astronomers, physicists, and philosophers alike. The idea that we might be part of a larger cosmic network laced with information, and perhaps even intelligence, is as exhilarating as it is daunting. Voyager 1 is not merely transmitting data. It is whispering clues about a cosmic architecture far beyond our current comprehension. The spacecraft itself remains an astonishing feat of engineering. Still powered by its decades-old radioisotope thermoelectric generators, it continues to operate against all odds. Designed in the 1970s with computing power that today would be dwarfed by a simple wristwatch, Voyager 1 now serves as humanity's most distant outpost. Its signal, a faint, ancient transmission traveling over 23 billion kilometers, represents our only direct contact with true interstellar space. Each bit of data it returns is a triumph of human ingenuity and endurance, delivering insights from a realm we may never physically visit. The fact that it continues to operate is not just a testament to NASA's engineering, but to human curiosity itself. Elon Musk, the founder of SpaceX, has spoken publicly about being captivated by Voyager 1's discoveries, calling its findings a wake-up call, a sign that it is time to take interstellar travel seriously. In Musk's view, Voyager 1 is not a relic of the past, but a beacon lighting the path to our future among the stars. He has suggested that these anomalies could even fuel breakthroughs in propulsion technologies, helping humanity develop the next generation of spacecraft capable of navigating and exploring these unseen galactic currents. The idea of riding these currents may sound fantastical today, but then again, so did powered flight a little more than a century ago. To Musk and others, Voyager 1's discoveries are not merely scientific curiosities, but calls to action, evidence that our destiny lies in reaching out beyond the confines of our solar system. These magnetic anomalies hint at more than just complex physics. They suggest that we are not passive observers in the universe, but active participants in a far larger cosmic story. Voyager 1's continued mission reminds us that exploration is not a destination, but a mindset. What began as a mission to study the outer planets has evolved into a quest, touching the very edge of known reality, forcing scientists to reconsider the nature of the heliopause itself. Rather than being a static boundary, the heliopause may now be seen as a dynamic, breathing interface where the solar wind collides with galactic pressure, where local and universal forces meet and interact. This revised understanding could fundamentally reshape our models of the solar system, our predictions of space weather, and our knowledge of how cosmic energy flows. As researchers continue to pore over the patterns in Voyager 1's data, plans are already underway for follow-up missions. These next-generation spacecraft would carry far more advanced instruments specifically designed to investigate the magnetic anomalies and energy structures that Voyager has hinted at. Such missions could finally confirm whether our solar system is part of a galactic web, a matrix of energy and matter linking stars, solar systems, and perhaps even civilizations. As these new missions are prepared, Voyager 1 remains a silent mentor, a trailblazer that showed humanity the way through the interstellar dark. Though its journey will eventually end, its power supply failing, its instruments falling silent, it will drift forever among the stars, a ghostly relic of human curiosity. Yet, the questions it has raised about the nature of space, the interconnectedness of stars, and the possibility of cosmic communication will continue to inspire generations. What are the true properties of the energy pressing against the heliopause? Could these forces carry the fingerprints of something conscious, intelligent, or at least more intricate than we have dared to imagine? These are not just scientific questions, but deeply existential ones. Voyager 1 forces us to confront the staggering scale and strangeness of the universe we inhabit. We live on a fragile, life-filled world orbiting an unremarkable star on the edge of a vast spiral galaxy. And yet, thanks to a spacecraft launched during an era before the internet even existed, we are beginning to glimpse the contours of a larger cosmic network. Voyager 1's faint signals from the edge of the solar system are not just streams of data. They are invitations, urging us to explore, to question, and to dream. As long as Voyager 1 drifts among the stars, humanity will have a presence at the interstellar frontier, reaching out with trembling curiosity toward mysteries that lie beyond. Its journey is our journey. Its discoveries are our discoveries. And in its ever-fading signal, we hear the cosmos calling us forward into the unknown. Meanwhile, the impact of Voyager 1's findings continues to ripple across the global scientific community, sparking wonder, but also a cascade of new questions that challenge long-held assumptions about our place in the cosmos. Its data suggests that the boundary between our solar system and interstellar space, the helipause, is far more complex and active than we once believed. Instead of a clean dividing line marking the sun's domain, the helipause may behave as a dynamic zone influenced by pressures, waves, and forces from far beyond our local galactic neighborhood. This new perspective carries profound implications. If the helipause is porous or responsive to external stimuli, then cosmic phenomena occurring light years away could potentially influence space, whether within our own solar system. Events such as supernova explosions, gamma-ray bursts, or even subtle fluctuations in the Milky Way's magnetic field might send ripples that deform or energize the heliosphere in unexpected ways. In this sense, Voyager 1's data serves as a kind of distant listening post, registering the universe's subtle pulses far beyond where the sun's influence fades. Particularly intriguing are the magnetic fluctuations Voyager 1 is detecting, signals that seem too patterned to be mere noise. Initially, scientists had expected the interstellar magnetic field beyond the helipause to be relatively uniform, shaped on large scales by the galaxy's overall magnetic structure. But the fluctuations Voyager 1 records appear rhythmic and persistent, almost like an electromagnetic echo from an unknown source. This has inspired bold new models, including the possibility that Voyager 1 is detecting interstellar turbulence, or even signatures of a kind of cosmic infrastructure, a lattice or framework of energy that links celestial bodies on a galactic scale. Such ideas were once confined to science fiction, but the concept of the cosmic web, a vast network of gas, dark matter, and galaxies interconnected like a universal scaffold, is now mainstream cosmology. If Voyager 1 is picking up microscopic signs of this structure at the solar system's edge, it might be our first physical evidence of the cosmic web's influence at a local scale. At the heart of these discussions lies an even more provocative possibility. What if these electromagnetic signatures are not entirely natural? Could they be evidence of ancient engineering, a subtle form of communication or control built by a civilization far older and more advanced than ours? While highly speculative, this idea has reopened serious debate about how intelligent life might attempt to signal across the galaxy. Rather than using traditional radio signals, which weaken over cosmic distances and timescales, such civilizations might embed information within existing galactic structures, using magnetic fields or currents as carriers, a strategy that would be far more durable and pervasive. For now, most scientists remain cautious, focusing instead on the physical mechanisms behind the anomalies. Voyager 1's instruments, despite being outdated, can still detect charged particles and low-frequency magnetic waves, offering an unprecedented view of the interstellar medium's composition and behavior. Meanwhile, Voyager 2, its twin, crossed the helipause in 2018 on a different trajectory, offering an invaluable comparison that has revealed variations in the boundary, shape, and pressure depending on location. This supports the idea of the heliosphere as an asymmetric, shifting interface, perhaps shaped like a comet's tail, influenced by galactic winds and pressures. Inspired by these discoveries, space agencies are now planning next-generation interstellar missions. Proposals for an interstellar probe, potentially launching in the 2030s, aim to travel even faster and farther than Voyager, equipped with modern instruments capable of mapping the heliosphere in 3D, measuring interstellar dust and magnetic fields with unprecedented precision, and exploring the very forces Voyager 1 has begun to uncover. As scientists analyze Voyager 1's cryptic transmissions, the craft's longevity itself remains one of its most astonishing feats. Designed for a mission lasting just a few years, it has survived the harshest conditions imaginable for nearly half a century. Its tiny plutonium power source weakens with time. Its instruments grow older and more fragile, and yet it continues to speak to us across billions of kilometers of emptiness. The simple fact that we can still hear its voice is a testament to human engineering brilliance, a quiet victory for perseverance and ingenuity that continues to pay dividends with every faint signal received. Yet, Voyager 1's mission is more than just a triumph of hardware. It embodies the idea that exploration is a fundamental human impulse, an expression of our need to know what lies beyond. It demonstrates that even the simplest, most limited instruments can unlock vast new realms of knowledge if sent far enough, patiently enough, with the right questions in mind. In its aging detectors, scientists glimpse not only strange magnetic waves and cosmic rays, but a future in which our species might one day navigate these interstellar seas in earnest. The Voyager program also stands as a symbol of international collaboration and shared wonder. Its data has not only advanced NASA's research, but has been shared across the globe, analyzed by scientists in dozens of countries. Its discoveries belong to all of humanity. The iconic golden record bolted to its side carries sounds, images, and music chosen to represent life on Earth. A greeting to anything or anyone who might one day find it. Or simply a message cast into the vast cosmic ocean for its own sake, a sign that someone was here and wanted to connect. As new generations of astronomers, engineers, and explorers take inspiration from Voyager 1, planning missions to the heliosphere and beyond, they are building on a foundation laid by this hardy probe. They dream of more advanced interstellar travelers that might one day journey to neighboring star systems, propelled by solar sails, fusion drives, or technologies not yet invented. Voyager's lessons about surviving the vacuum, recording data with minimal power, and communicating across light days of distance will guide them all. Even when Voyager 1's final signal is lost to the noise of the universe, its journey will continue. It will drift forever between the stars, a silent emissary of Earth and proof that for at least one brief moment in cosmic time, a small blue world dared to wonder what lay beyond its sky and found a way to ask. In this way, Voyager 1's lonely journey through the darkness is not ending, but laying the foundation for a new era of exploration. Its faint, persistent signal will continue to echo in human imagination,